Hey, what's up guys? So we're going to be looking at the exponent rule that allows us to subtract the exponents whenever we divide powers with like bases. Here it is. Alright guys, before we get into the rule, I want to cover some vocab real quick. So here we have an expression that says 5 raised to the third power. Now the entire expression is what we call the power, and then the base is the big number here, and then this little number up in the corner is what we call the exponent. And the exponent tells us how many times the base appears as a factor within a product. So 5 to the third power we can express as 5 times 5 times 5. Alright, so with that said, here's the rule itself, and what the rule says is that if we have x raised to some number n power, and we have x raised to some number m power, and we divide these powers, we can express that as that base, x in this case, raised to the power of n minus m. So basically, if we're dividing powers with like bases, we can subtract the exponents. That's basically all this is saying. And now it's very important to remember that you need like bases for this rule to make any sense, meaning this number has to be the same as this number. Alright, so let's go ahead and get into an example here. Let's say we have a raised to the fifth divided by a to the second. Alright, so since we have like bases, we have a raised to something and we have a raised to something and we're dividing, our rule says we should be allowed to just subtract these exponents. So we should be able to express this as a raised to the third power, because 5 minus 2 is 3. Now it's important to understand why this is the case, so this rule doesn't just become something you have to memorize. So a to the fifth we know means a times a times a times a times a, right? And a raised to the second power, or a squared, we know means a times a. So what we have here is we have a chain of multiplication, a product, being divided by another chain of multiplication, by another product. And so since we have factors that are the same in the numerator as we have in the denominator, we can make some cancellations. So a divided by a, well, that's just 1, right? So we know that those factors will cancel out. And now there's another cancellation that can take place, right? We know that a divided by a is just 1. So those factors will cancel out. And so both of the factors of a canceled in the denominator, which means there's just a 1 left. There's that invisible 1 there. And then we have 3 factors of a in the numerator. So we have a times a, all divided by 1, which we know is just a times a, or in other words, a to the third power. So this is why the subtraction rule takes place, because it's really just how many of the factors are canceling. And this also sort of illustrates why the bases have to be the same, right? Because if these bases weren't the same, then they wouldn't cancel, right? They only cancel if you have something divided by itself. All right, so let's go ahead and move on to another one. Say we have x to the third divided by x. All right, well, we know that x is just x to the first power, right? And so our rule tells us that we should be able to subtract our exponents since we have like bases here. And so 3 minus 1 is 2, so we have x to the second power. And again, just to illustrate where this is coming from, we know that x to the third is x times x times x. And then we just have one factor of x in the denominator. And we see that there's going to be a cancellation that takes place. X divided by x is just 1. And so we have just 2 factors of x in the numerator divided by 1, which leaves us with the x squared. Now, illustrating this out for large exponents isn't going to be practical for us. So this is where the rule becomes sort of important, because when we have examples like this where we're dealing with large exponents where it's not reasonable to write it out all the time, if you recognize that we have like bases, which in this case we do, the base is 5 in both of these cases, well then we know that in the numerator we're going to have 20 factors of 5 being multiplied together, and then in the denominator we're going to have 15 factors of 5 being multiplied together. And so 15 of those 5s are going to be canceled out, right? 15 of the 5s here in the numerator are going to be canceled by the 15 5s that are in the denominator. And so again, that's where this rule comes into play. And we would be left with 5 to the 5th power, because 20 minus 15 is 5. All right, now I want to sort of cover a bit of a more complicated example. Say you have an expression that looks a bit more involved. Okay, you might have an expression that looks like this, where you have multiple variables, multiple bases, okay, and maybe even some constant factors out front here. But remember, this is just a giant chain of multiplication, right? This means 15 times x times x times x times y times y times y, blah, 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 right? And then down here in the denominator, this means 3 times x times x times y times y. So it's just a giant product in the numerator, a product in the denominator, and then we're dividing these two products, right? So we can use our exponent rule for the variables, but then we can also simplify the 15 divided by 3 as well. And so 15 divided by 3 is just 5, right? And now we can use our exponent rule for the like bases. So if I have x to the 3rd and I see an x to the 2nd in the bottom, I know that 2 of those x's are going to cancel. So 3 minus 2, that's going to leave me with just x to the 1st, or just x. And then again, these 2 factors of y down in the denominator are going to cancel 2 of the factors of y in the numerator, which leaves us with 3 factors of y in the numerator. And again, our exponent rule is that 5 minus 2 gives us the 3. And so this quotient, this expression here, just simplifies down to this. All right, and with that said, guys, it's been demonstrated.